Okay, let's begin our lesson. So please help to wake up your classmates, okay? Okay, it's a very sleepy and today's weather is so good. So I also want to go to take a nap. Okay, so it's kidding. But I only sleep for 3 hours. It's very weather for me. Okay, so let's go back to our lesson. When we talk about the middle end of the line and the back end of the line, and first you need to know. So this is all the metal line. How you see, this is the metal line, but between the metal line is the outside. Okay, so you see how between all of the metal line is the outside. Outside is the white area, the white region is the outside. Okay， 白色的区域全部都是氧化物。So this outside, the purpose for this outside is to isolate between two metal lines, Okay, so you see the white region is the outside. Okay, and L means local, I means the interconnect 内连线，好，金属内连线。Interconnect 内连线 in industry we also call it interconnect. Interconnect just like a metal line, but in industry we don't say metal line. But in order to let you understand, I will say metal line. But in industry we prefer to call it interconnect. Okay, so I also recommend you to memorize interconnect. 好，内连线，金属的内连线 interconnect. Okay, connect, you want to connect something, or you want to connect all of this electrical signal by using the metal line. So interconnect will be a metal material, So interconnect, just like the tungsten we mentioned here, or the copper, all of this metal line. M4 is the false metal, the metal layer. M4, M5, M6 is the metal layer, the metal layer of the metal. We call all of it is the interconnect. Between two interconnect is our outside. And the textbook write down ILD, this D means dielectric, 介电层 D means dielectric. Okay, but you will just say it's the outside layer. I think it's fine. Outside layer, dielectric layer is the same thing. The same thing. Or you can say it's the dielectric 介电层, or it's just the outside, the insulator. Okay, or we will say it's a dielectric or it's the outside. But you know it's just a insulator. Okay. Okay. So right now, we talk about the damascene, how to fabricate the copper, interconnect. We need to use the damascene process. Okay. So I just show you the most important concept of the damascene. Okay. And all of the detail how you can learn when you go to industry. But some important concept I will show you. Okay. So we mentioned today, if I want to have the final pattern like here, I want to pattern the copper or the copper metal line. Just like, for example, if I want to pattern, for example, those two metal line, okay, those two copper metal line here and here, okay. So I mean, our final pattern is copper here and the copper here, okay. So how can we achieve this? So we mentioned earlier, today, we cannot deposit our electroplate. We cannot deposit our electroplate copper first. We cannot do that because we don't have any solution to etching to remove the copper. Okay, so the first methodology is not right. Okay, how about the second one? The second one here, and the first process flow, we need to deposit. We need to deposit SiO2. We need to deposit SiO2 first. Okay. So right now we don't deposit copper first. Right now we deposit the outside first. So deposit the outside first. Okay. And then we define the pattern for the outside. Right now we can define the pattern for the outside. Why? Because we can etching the silicon dioxide so easily, right? We can etching, how we can etching silicon dioxide so easily. So today we deposit the oxide first, and then we use the photolithography. We use the mask, photo mask, to define the pattern of the SiO2, and then we can remove the central region of the SiO2 so easily. So that's the reason we can etching silicon dioxide so easily. So that's the reason we deposit SiO2 first, and then we etching silicon dioxide, okay? So right now, after we etching the silicon dioxide, we fabricate the space, we generate the space for the copper to fill in, right? Oh, right now, after we etching silicon dioxide, we fabricate the space here, we fabricate the space here, so later the copper can fill in this space, okay? So right now, oh, the next step, we electroplate copper, 电镀, we electroplate the copper into this space, okay? So right now, after we electroplate the copper, so the copper will become like, oh, thank you for your help. Oh, very good. Oh, very good. Okay, so right now, oh, the next step, after I have the pattern for SiO2, so I electroplate the copper, okay? After we electroplate the copper, you see how the profile is high, low, and high, low, right? So how should we do? We use the CMP, or CMP copper, oh, so we can remove the copper layer by layer, layer by layer. So right now we use the CMP to remove the copper layer by layer. Okay, so right now we remove the copper, or we remove the copper because we want to have a very flat surface of the copper. So we need to remove the copper by using CMP, and we can remove the copper layer by layer. Thank you very much. Thank you. So finally, you will have the pattern like the right curve here, right? Copper is here, and the other copper is here, right? Can you see that? We have the copper here and the copper here. It's our final pattern of our copper, right? So you see, if I use the first one, sorry, the second method, you see, I didn't need to pattern the copper, right? I didn't need to etching the copper, right? The only thing I do for the copper is electroplating copper, and then I use the CMP, right? I don't need to remove. I don't need to use the wet etching or dry etching to remove the copper. I only use the CMP, right? So right now, oh, you can have the concept. We need to fabricate the space, fabricate the hole for the copper. Then we just deposit the copper. We electroplate the copper into this small area, okay? And then we can have the pattern we want, okay? So for the second method, we call it damascene. damascene 就是它先挖一个洞，它先把你要填的地方把洞挖出来，把你要填铜的地方那个洞先挖出来，最后把铜填上去 ，CMP 磨平，就完成了 ，OK。所以它不是这样，它不是全部长一层铜再去做pattern，不是它是把它要填的地方挖洞，挖完洞之后把铜填进去，最后用 CMP 磨掉就可以了，OK。So for the damascene, I can write down for you. For the damascene, how can we do that? We deposit the oxide first, and then we etching, we etch ETCH, we etching oxide. We deposit the oxide first, right? And then we etching the silicon dioxide, right? And then we deposit or we electroplate the copper into this small hole, okay? Of course, finally, we need CMP or we need CMP copper, okay? Also, for the damascene process, it means we need to deposit the oxide first, and then we etching the oxide in order to fabricate, in order to generate the space for the copper to fill in, okay? Then, once we have the space for the copper can fill in, just like the copper can fill in the space here and the space here, okay? And finally, we use the CMP or CMP. So after we use the CMP, then we will have a very smooth, very flat surface, okay? So this process is the damascene, or is the concept for the damascene, okay? Or maybe we don't have time to go through the metallization. I think it's a simple chapter, but we don't have time to go through the metallization. 金属化的制程我们可能没有时间，我们可能之后也不会上到金属化的制程，但是它全部的制程都在讲什么？都在讲这个大马士革的方法。所以有时候你记得 concept 是比较重要的。那 detail 未来你看课本或是你阅读一些文献或是你有到这个部门工作，你其实自然就会用到了。OK, we just show you the concept for the damascene, okay? It means we need to deposit the oxide first. We need to pattern the oxide and then create the space for the copper to fill in. Once the copper fill in, then we use the CMP to have a very flat surface, okay? Okay, so for this page, we need to deposit the oxide first, okay? So here, let me see. And first, we go to the thin film module. We use the CVD to deposit the nitride. And this nitride, the purpose of the nitride is to protect the transistor. Active region is the transistor region, right? Okay. And then number two, we also go to the thin film module, because right now we also use the CVD, right? We use the CVD to deposit nitride. We use the CVD to deposit the oxide, okay? Because I mentioned I already show you 90% of the chance we use the CVD in the IC fab. 90% of the process for the thin film they use the CVD. So you only need to remember when do we use the PVD, okay? 在业界大概90%，你只要猜 CVD 就对了90%，不是一半。你在业界到底我们去新film的部门，到底是用 CVD 还是 PVD？ 你猜 CVD 对了90%，所以你只要记剩下的10% PVD 物理气象沉积什么时候用？我要长很纯的金属的时候用，什么时候？刚刚我们是不是在长 contact 的时候要先长一层金属 TI？ 我做 TI silicide 要长 TI， 我做 nickel silicide 要先长 nickel。是不是你在长那一层金属，因为要降低 contact resistance， 所以那时候你才会用 PVD， 其他的90% 全部都是 CVD， 所以业界大部分是 CVD， 这个是没有错的。So 90% of the chance in IC fab, they will use the CVD, they will use the CVD tool, chemical vapor deposition. It means the deposition involves some chemical reaction, okay? Only 10% they use the PVD because they want to have a very pure metal layer, like the TI for the silicide, or like nickel for the nickel silicide as a contact material, okay? Okay, so right now, we use the CVD, we only locate it in the thin film module. And right now, we also use the CVD to deposit oxide. So right now, oxide. So you see, number two, we need to deposit the oxide. After we deposit the oxide, as you see, let me see, the profile like this. High, low, right? Because we have the gate, because we have the gate region here, we have the gas region here, so the profile is higher for these two regions. Okay, so number 2, we go to the thin film module, we use the CVD to deposit the oxide. Okay, but here I just also want to show you why does the textbook show you we need to use the low K material. Right now we talk about this oxide. This oxide, the purpose for the oxide is only for the insulator. Okay, insulator between two metal layers. Okay, so do you still remember when we talk about the equation for the capacitance? C is equal to epsilon 0 epsilon r times the area divided by D, right? And where is the K? For low K, why do we want the low K? Low K means we want the low epsilon r. This K is the epsilon r. In school, professor will show you epsilon r is the dielectric constant, right? In industry, we don't say epsilon r, too long. We say K. In industry, we say K. We don't say epsilon r. But in the textbook in school, I know you learn the epsilon r, dielectric constant of the material, right? But however, in industry, the dielectric constant for the oxide will be K. We just say K. K is the dielectric constant, 介电常数 dielectric constant for the K. Today, if I have the lower K, it means the lower epsilon r, then the capacitance C will be lower, okay? And right now, I need to have the lower capacitance because it will result in the smaller RC time delay, okay? If you have the smaller RC time delay, then it means the frequency of the chip can be higher, the speed of the chip can be improved, can be faster. So that's the reason for the oxide, we need to choose the lower K oxide in order to have the smaller capacitance. Then it will result for the smaller RC time delay, okay? So right now for the lower K material, many years ago, I can show you, originally we used the SiO2 but however, after that we choose to, I know SiO2 is the very common material we use. However, the dielectric constant for SiO2 is 3.9. It's 3.9, okay? And then the textbook show you we use the fluorine dope, SiO2. K is around 3.7, okay? Fluorine dope SiO2, okay? And then Intel, Samsung, and TSMC, they use the carbon dope oxide, carbon dope oxide, okay? They use carbon dope oxide, and they time the dielectric constant can further improve, to around 3, and Intel call it carbon dope oxide, okay? This is called by Intel, or maybe other company, I don't know, Samsung and TSMC call, but the Intel call it carbon dope oxide, because we have the carbon into the silicon dioxide, okay? So at that time, the dielectric constant is 3. And right now, the technology node is moving on like to 45 nanometer, okay? Right now, it's like the 45 nanometer technology node, okay? So we use the carbon dope oxide, SiCOH, okay? For me, I prefer to call it SiOCH, because for me, it's much more easier to remember. Okay, for me, I prefer to call it, but it's not so accurate. It's not so accurate, because I know we can use the CH3 or CH3 bond to replace of the one oxygen, so it's more easier for me to memorize. But if you want to write an accurate equation, it's better to write down SiCOH. Okay, it's a carbon dope oxide. Okay, carbon dope oxide. Okay, we still use the main material is the SiO2, okay? But right now we use the CH bond, we have the CH3 group. to replace of the oxygen, okay? But until right now, we don't have any material to change, right? Or we change the material, right? So until right now, we change the different material. The K, when the K smaller than 3.9, we say all of this is the low K material, When we talk about low K material, right now we talk about the oxide in the interconnect, okay? When we talk about high K material, we talk about gate oxide, okay? When we talk about low K material, we talk about the oxide in the interconnect, okay? 好 ，high K material， 我们说 high K material 是在讲 gate oxide， 我们说 low K material 是在说哪里？是在说现在后段内连线里面的氧化物 ，OK？ 哦，所以 high K 跟 low K 指的是不同地方。When we talk about high K material, it means we talk about gate oxide, gate oxide. When we talk about low K material, we talk about the oxide in the interconnect, OK？ 哦，所以同学不要搞混哈，它不是用在同一个领域里面，哦，不是运用在同一个地方 ，OK？So until right now, we choose the different material in order to lower the dielectric constant from 3.9, the ideal value, to the 3, okay? Oh, but right now, we cannot find another material. Until right now, we don't have the good material. So until right now, we need to change the structure. How can we change the structure? And first, we use the porous. We use the porous structure because the porous structure has less dense. The density is lower. The density is lower. So at that time, right now the dielectric constant is around 2 point some, 2.4, 2.5, 2 point some. Just for example, around 2.5. Porous, it means the less dense, less dense, 比较不致密，没有这么致密 less dense. Or you can say the density is lower. The density is lower. We can fabricate some porous on purpose. Then the dielectric constant can be lower to 2.5, around 2.5. Okay. But right now, we still want to further reduce the RC time delay. How can we do? I believe this is the final solution. I believe. Right now, we want to achieve K small, very near 2. How can we do? Air gap. Air gap is the technology. You will hear it very, very often in the industry. So I recommend you for the final one, you need to memorize. I hear air gap not only in the interconnect, also for the sidewall spacer. We also use the air gap technology. What does that mean? It means we introduce air. We introduce air into the dielectric. We introduce the air into the dielectric because the air has the dielectric constant of 1, right? Or we push the air into the dielectric into this material, and you know the air has the dielectric constant of 1, right? Air has the dielectric constant of 1, so we push air into this material, SiCOH. So we call this technology as the air gap. We put air into the material. We put the air on purpose into this material, so the dielectric constant can be further reduced to around 2. OK？ 因为空气的介电常数是1，所以今天我只要在这个材料里面，我可以把这个把空气我们制造我们在这材料里面制造一些奈米的这孔洞，然后让它里面有产生这些空气。这有空气的话，那它代表说这个材料里面材料的本质，它的 dielectric constant 就会降低。So our goal is to achieve the dielectric constant of 2. Okay, so that's the reason we need to generate, or we need to induce the air into the outside. Okay, and the outside material we still use this one, SiCOH. Okay, but the structure is changing. The structure, we can use the porous. And then recently, we already use the air gap. So today, if I want to reduce the RC time delay, I choose this material, okay? And then I choose this structure, okay? So you need to remember the air gap or the air gap. The purpose for the air gap is to reduce the dielectric constant for the lower K. So if you want to reduce the RC time delay, how can you do? Choose the accurate material and choose the accurate structure air gap, okay? So air gap is not only used for the interconnect, but also you see on the sidewall spacer here, the sidewall spacer here, right? The sidewall spacer here, we also has the outside, right? The sidewall spacer or the outside between this between the source or between the source, the drain, or between source and the gap, or the outside between here or here. We also induce the air gap, or we also use air gap technology in order to reduce the RC time delay. 所以 air gap 这个技术不是只有用在后段内连线它在连做电晶体旁边的 outside， 其实它都可以用 air gap 的这个技术来做。所以有时候你听到 air gap 在电晶体的时候，你也会听到，因为电晶体旁边有很多 sidewall spacer， 那这边也是2条金属线嘛，只要有金属线的中间，这个 outside 我们都会倾向用 low K 的材料，去避免这个 RC time delay 太长。所以 air gap 可以用在电晶体的周围，也可以用在这个 interconnect 的里面的这些绝缘层。OK， OK， so this slide I just want to show you how can we reduce, how can we use the low K or low K material. OK, and SiOF right now we don't use SiOF, it's a very long time ago, so we don't use SiOF. OK, and then we need to use the CMP. Why do we use the CMP outside? Because later we need to do the etching. So when we want to use the photolithography, we need okay. So right now, do you need to copy this one? You already write down? Okay, let me move on. Okay. So right now, after we deposit the low K outside, and then we need to do the CMP first. Why do we need to use the CMP first? Because you see, the next one, we need to go to the photolithography. So before we do the photolithography, I need to make sure the surface is flat. Okay. Before we do the photolithography, I need to make sure our surface is flat. So I can do the photolithography. OK， 我们在做黄光微影之前，因为我们是有用光，我们用光学有跟景深有关，所以你必须要有平坦的表面。So today, before the photolithography, we need to have a very flat surface. So that's the reason before the photolithography, we need to use the CMP to obtain a very flat outside. Okay. So let me see. So right now we have a very smooth outside. Okay. And then we go to the photolithography. We need another photo mask. Okay. And then we need to pattern the outside. We need to pattern the outside. Let me see. So later we need to have the PR here. We need to have the PR. So later we need PR here. Okay. So later I need a mask. Okay, I need the mask. So this is the mask, the photo mask, the pattern for the photo mask. Okay. So after I have a very flat outside here, very flat outside. So the next step, I can go to the photolithography. So I use the photo mask to define the pattern. So this is the pattern for the photo mask, okay? And then, the central region, we have the UV light. UV light will pass through the central region. So the central region of the PR here is removed. PR is removed. The PR is removed here. So finally, we can define the photoresist PR pattern. It's the same as the photo mask. Okay, so the same pattern Okay, so right now, right now we have the PR on the top of the outside here. So this outside can be protected by the photoresist PR. Okay, so the next one, we go to the etching process. Etching process. So we can remove the outside without PR protection. Okay, so we can we want to remove here. We want to remove the outside. Okay, we can remove the outside because all of this region. Or we can remove the outside here, remove the outside here, remove the outside here, because here we don't have the PR, or the PR cannot protect the outside here. So that's the reason the central outside here and here is removed. Okay, just like we mentioned, right now we can fabricate the outside pattern, like the second step. Okay, so right now we can fabricate the pattern, just like the second step here. Okay, so the next one, right now we need to, right now we want to put the tungsten into, this hole. Okay, so right now I need to use tungsten because this is the beer, this is the beer or plug. This is the first metal we are talking about, right? So right now I don't use copper, I use the tungsten, okay, because this is the first layer. You can see this is the first layer. So I need to put the tungsten here, okay? But you need to remember, before you doing that, you need to deposit the TI first. And then the second one, you need to deposit the TIN. Then final one, you can deposit the tungsten. Or you can deposit the tungsten, okay? So today, so this is the outside, okay? So today I want to deposit, I need to deposit the TI first. A very, very thin layer, the TI first. And the purpose for the TI is the adhesion. Because TI is a pure metal, right? Pure metal is very easy to be oxidized with the outside, right? So if I put the TI here, TI can be oxidized by SiCOH. So it's very, TI can be a very good adhesion layer between tungsten and the outside. So that's the reason you need to remember, we need to use the TI first, okay? This is the concept. Today, if you want to build an adhesion layer, 附着层 adhesion layer, you need to use the pure metal, okay? This concept, we will use it again, okay? The first one, adhesion layer must be pure metal. 纯金属容易氧化，氧化跟谁氧化？跟你的阿塞氧化，跟阿塞氧化表示它的氧的原子会跑去 TI， 会形成 TiO 的键结，形成 TiO 的键结可以帮助它有比较好的附着力，所以附着层为什么都是纯金属？So today we use the TI for the adhesion layer because TI can react with the oxygen here and to form the TiO bond. So that's the reason TI can be a very good adhesion layer. That's the reason the first processing step will be TI. Okay, will be TI. TI is the first layer, very thin layer. Okay. How about the second one? The second layer. The second layer I use the green. The second layer is the TIN. The second layer is the TIN. Okay. The second layer is TIN. The first layer is the TI. And what is the purpose for the TIN? TIN is a diffusion barrier. Who can diffuse? Right now, the third process, we need to CVD tungsten, all right? Finally, we need to have the tungsten inside, right? So who can diffuse? Tungsten can diffuse out. Tungsten can diffuse out. So today, we need to use the titanium nitride. Titanium nitride, you see? TIN again, right? Oh, I show you. Ti is a very important material in the IC fab, right? So right now, adhesion layer and the diffusion barrier, we also use the Ti, right? So Ti for the adhesion layer and TIN for the diffusion barrier. They have a different purpose because TIN is a very strong material because titanium is bonding with the nitrogen. It's a very strong bonding. So TIN is a very robust, very strong material. So that's the reason it can be a diffusion barrier, okay? So where is diffusion barrier? The green layer, TIN, or the second processing flow, you need to deposit the TIN, okay? And then the tungsten will not diffuse out, okay? We don't want the tungsten diffuse to the transistor, okay? We don't want the tungsten diffuse to the transistor. Then the transistor will be failed. So we need to stop diffusion, tungsten diffusion. So that's the reason we need to use the TIN, okay? So right now, the material system, you need to remember, I write down for you. So right now, we talk about the tungsten, right? But one day, if I want to talk about the upper metal, like the copper, how should we do? It's also, for example, it's IOCH outside layer. Or right now, if I want to talk about the copper, so you need to know the first layer. The first layer, adhesion layer for the copper will be TA, okay? And then, how about the diffusion barrier? Diffusion barrier will be TAN, okay? So right now, the metal, here, the metal will be copper, okay? Likewise, TA is the diffusion, TA is the adhesion layer for the copper, okay? And TAN, the green, the second layer, the green layer, TAN is the diffusion barrier, 防扩散层. TAN is the diffusion barrier for the copper, okay? We only have those two material systems, okay? So I need you to memorize it, okay? It's very useful in industry. When we talk about tungsten, we will use Ti and TIN. When we talk about copper, we will use TA and TAN, okay? So there are only two material systems we use for our interconnect, okay? And also, the second paragraph here shows you tungsten is preferred over aluminum and over copper due to its ability to fill holes, due to its ability to fill the small contact hole here without leaving void, okay? So we can fill the copper into a very small space, like into a very small contact hole here. So that's the reason we will use the tungsten here, okay? So this one just, this slide for, just for your reference. I mean, many years ago, we used the aluminum because the contact hole is very large, large contact window, large contact hole. So we can use the aluminum, okay? Before, when the technology no larger than 0.18 micrometer. So many years ago, maybe before 2000, okay? And then what happened? When we talk about when the scaling down, when the transistor becomes smaller and smaller, also the contact hole becomes smaller. So if we still use the aluminum, then we will have the void. OK， 因为铝的填洞能力很差所以它最后会留下一个 void because it has a very poor ability to fill in the small hole, so it will leave the void inside here. OK, so that's the reason we use the tungsten. We use the tungsten here because tungsten plug can fill in the small contact hole. OK, so we can call it tungsten plug. OK, tungsten plug 我们就习惯叫它 tungsten plug。这个中文也不太会翻可能这样，这个我不太会翻我们都叫它 tungsten plug。OK， 有不知道是不是电源的，这不太会翻Anyway， 就是 tungsten plug。OK， so the next one we will talk about the VL1 formation. Where is the VL1? We talk about before the VL1, we need to deposit the dielectric. ILD, interlayer dielectric ILD. So ILD is here in the yellow region, OK? And also we will fabricate the VL. VL is the blue one. Blue region is here, OK? So the yellow region is the insulator, interlayer dielectric ILD. And blue region is the VL, OK? So the purpose for the ILD is the insulator between two metal lines, OK? And the VL is the metal line. So it's the electrical pathway from one metal layer to adjacent to the next metal layer. Okay. So likewise, we need to go to the thin film module. We need to deposit the oxide and then do the CMP. After we do the CMP, we can use the photolithography to define the oxide pattern, and then we do the etching. The same process flow as we mentioned here, OK? 后面的制程都一模一样它的制程全部都一样So right now we can define the oxide pattern. We define the oxide pattern just like the processing tool here. We etching the silicon dioxide, OK? And then the next one we need to put the metal. Here is the tungsten. We put the tungsten into the gap between the oxide. So right now we still need to use the tungsten plug. Where is the tungsten plug? Here. We call it the tungsten plug. The blue region is the tungsten plug. So before that, you need to know we use Ti first, the TIN, and then it's followed by the tungsten. Okay. And of course, just like the copper, we need to CMP in order to have a very smooth surface, okay? So you need to know until right now, we need to deposit the oxide first, and then pattern the oxide. Then we can deposit our metal like the tungsten or the copper inside the gap between the oxide, okay? And this process we call it damascene process, 大马士革的方式所以下面的这些制程其实都一直重复，用的都是大马士革的方式先长oxide，然后 pattern oxide，然后做出孔洞空间来之后，我们再去长我们的金属 ，OK？ And I can show you right now due to the scaling what happened when due to the Moore's law, what happened when the tungsten plug becomes smaller and smaller. Originally you can see for the tungsten plug, maybe the first layer and the second layer is Ti and the TIN, right? Ti and the TIN, and for this Ti and the TIN, 5 nanometer each, okay? So for the tungsten cross-section area, I still have like for example 19 nanometer, for example. And this data is from the technology node of 22 nanometer technology node for the chip for the 22 nanometer technology node. Okay, So it means the tungsten still occupy, it still occupy 90%, okay? So if I write down the percentage around, okay? For the tungsten percentage is like 90% is covered by tungsten, okay? However, Ti and TiN also occupy another 10%, and the Ti and TiN has the higher resistivity, right? And the tungsten has the lower resistivity, okay? But however, what happens when the technology node is moving forward? You see, when it's scale, when the scale down happens, right now, the change, this is the structure. So right now, after the Ti and TiN, after we deposit the Ti and the TiN, Ti and TiN, maybe it's very difficult to scale down for the Ti and the TiN because it's only 5 nanometer, okay? And right now, how about the tungsten? Just for example, right now the tungsten only 30 nanometer. Sorry, the ratio is a little bit strange, okay? But don't worry about that, okay? Right now, you see, the tungsten is only 70%, 75% is tungsten, right? And the Ti and TiN occupy another 25%. So when you see, the percentage is changed. So right now, because we must have the adhesion layer and the diffusion barrier, so we must deposit Ti and the TiN before the tungsten. But what happened when we want to scale down, like the 40 nanometer, nowadays, the metal light pitch is 40 nanometer nowadays. So you see, when the metal light is only 40 nanometer, just like right now, the tungsten only occupies 75%, okay? Because you cannot scale down the Ti and TiN. I think this is the minimum thickness for the Ti and TiN. So you see what happened of the resistivity of the interconnect material? What happened to the resistivity of the interconnect material? What happened to the let me show you what happened to the resistance, because this is the metal light. So resistance of the metal light, what happened? What happened to the resistance of the metal light? 这是金属线的电阻。我们现在在讨论的是 interconnect 就是金属线，所以我们现在讨论的是金属线的电阻。So what happened? 22 nanometer. This is the scale for the 22 nanometer. This is the scale for 5 nanometer technology node, for example. So what happened when the technology node is moving on from 22 to 5 nanometer technology node? What happened? You see the same material, right? The same material, but the structure is different, right? Structure is different. So like the 5 nanometer technology node, this chip, the tungsten is only occupied for the 75%, but the tungsten has the smaller resistivity, right? But however, the percentage is smaller. It means the total resistivity of this interconnect will be increased. Okay, because the tungsten percentage is lower, so the total resistivity will be increased, right? The total resistivity of those interconnect will be increased, because the tungsten occupy the smaller percentage of the area of the volume, okay? So the resistivity of the interconnect will be increased, okay? And how about the cross-section area A? You see, the cross-section area A is also smaller, right? The cross-section area A of this one is smaller, right? So A is also smaller, right? The area is also smaller. So it will show you the resistance will be increased a lot, okay? Resistance of this structure will be increased a lot, okay? Due to the material, the overall material will have a higher resistivity, and the cross-section area here, will be smaller, so it will result a higher resistance for the nowadays interconnect. So nowadays the interconnect will have the higher RC time delay. It will have a higher RC time delay. So that's the reason. How can we solve this issue? Of course, you cannot reduce the R. Very difficult. So why do you need to use the low-K material? Because you want to reduce the capacity. Okay. So I just want to show you for the trend for the resistance of the interconnect. OK。我们微缩的时候，金属线的电阻一定会变大。为什么？你从两个面向，材料的 resistivity 跟 cross-section area 都会降低。resistivity 增加 ，cross-section area 降低，所以导致金属的导线会增加。所以金属的电阻会增加。所以这为什么我们要使用 low K 的材料？降低你的这个寄生的电容。你的寄生电容降低后，我们才能让 RC time delay 维持在一个比较可以接受的范围。OK。That's all for today's lesson. Okay. Any question you can discuss with me. See you next week.